no sense. So I need to set up a bit of a context. So the first section is about recognizing sequences. I want to show what I mean about sequence recognition. To do this particular type of sequence recognition, we use a certain type of finite automata, which I will explain. To do it, the particular construction that's interesting, we use a technique called the Brzezowski derivative, which again I have to explain before the context for the particular algorithm will make sense. And at the end, I have some experimental results that were satisfactory. Okay, what do I mean by regular sequences? So when you look at this sequence, what we have is a symbol followed by some numbers, or a symbol followed by some strings, and then these subsequences concatenated together 0 or more times. So exactly what type of sequences are we talking about? Well, you can describe these as regular expressions. So a symbol concatenated onto 0 or more numbers or 0 or more strings, and that whole sequence may be occurring 0 or more times. If you express this in common Lisp S expressions, it looks like this: a star of a cat of symbol and a star of et cetera, et cetera. So how do we know if a sequence matches this expression? Well, what you need is a finite automata corresponding to that expression. How do we create that finite automata? Ignore that fact for the moment and just assume that it's been given to us by God. And we want to know whether the sequence matches the regular expression in terms of a computation. So the way we do that is we start in state 0. We look at the first element of the sequence, which is a symbol. We follow the symbol arrow. And we see the next element is a number, so we follow the number arrow. We have another number, a symbol, string, symbol, string, symbol, number, 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 symbol, number. And then we end up in a designated state with the 2 circles, which means that this is an accepting state. So the sequence does match the expression. If anything else happened, for example, we have a missing transition, we encounter a list, we don't have an arrow for list, or if we finish the sequence early without being in a final state, then the sequence does not match the expression. Sometimes a finite automata can be non-deterministic, as we see here. The arrows leading Q0 are float and number, but any float is also a number. So we want to avoid situations like this, which are non-deterministic. We'd rather have deterministic finite automata for reasons which I'll be able to, well, happy to answer in the Q&A part, if you like. But we want to be able to generate finite automata which are deterministic, that have no ambiguous transitions. The common Lisp type system works quite well for this application. So types in common Lisp behave like sets. So and we have this function called subtype P, which we can ask questions about types, such as the subtype relation. So we can ask, is float a subtype of number? Is unsigned byte and fixed num a subtype of rational? Does the intersection of rational and float contain something, or is it empty? And we see from the diagram there that in fact float does not intersect rational. But unfortunately, sometimes subtype P returns don't know. So it either returns yes, no, or don't know, in the cases that it could not prove or disprove the question. So the question now is, how do we construct these finite automata? So this quite scary looking slide, what I want to express here is that we're given some rational expression or some regular expression at the top involving concatenation, stars, unions, intersections, and so on. We want to start with, I don't have a laser pointer, with R0 corresponding to that expression, and then we derive other regular expressions from that using this blue symbol, the derivative of R with respect to X. Each time we evaluate that, we get a new regular expression, which we associate with some new state, and that's how we generate new states in the finite automata. And whatever type we used for x, the derivative of some regular expression with respect to x, becomes the transition on the finite automata. And we keep evaluating that expression, that operator, on all new regular expressions until it terminates. And it will eventually terminate, and you'll have all of the states and all the transitions. So we have some set of input types which are labeled as A, A1, A2, A3, which come directly from the regular expression. And we want to derive a set of types, which is a partition. So string, integer, and number and not integer, which I label as X. Two things you don't know yet. One is, how do I actually compute the derivative? And two, what are the values of X that we need to use for the transitions? So first I want to talk about how to actually compute the derivative. And it's not actually so important to understand the semantics, because the algorithm is very straightforward for doing the computation. So we take a regular expression, such as R here, and then we apply a certain set of recursive rules. So if we have the union of two expressions, R and S, the derivative of the union equals the union of the derivatives. Same for intersection and same for the complement. For the conjunction, R dot S, so conjunction, concatenation, R concatenated with S, we don't simply have the concatenation of the derivatives, but we have to do a little bit of juggling. The derivative of the first concatenated with the second, union the derivative of the second. So this just fills out a recursive function that descends the expression until it reaches the leaf levels, and the expression has to terminate. And when it terminates, you will notice that we have common Lisp types. The terminal elements are number, string, and integer. And one of these two relations has to hold. Either X is a subtype of A, or X intersected with A has to be empty. And if these hold, then we can compute the finite automaton. But sometimes A might be a proper subtype of X, which means that we haven't done our work correctly. We haven't partitioned the types in a way that this relation holds. Or worst thing that can be is we constructed types, but in the end, subtype P can't tell us yes or no, is the subtype relation valid. So now we know how to construct the finite automaton, but we need to know which values of X that we use for the derivative. So given the set of types, we want to start with the set that's given, integer, number, and string. And we want to compute this partition, so number and not integer, integer and string. And these types obey several attributes. The union is preserved, so the union of integer, number, and string is the same as the union of number, number and not integer, integer and string. So the union is preserved. The types are disjoint, so all of the values, the types X, are disjoint from each other. There is no ambiguous set of types. And all of the X's are either subtypes or disjoint with all of the A's. So if you choose any X and any A, either the subtype relation holds or they're disjoint. We never have partial intersection. So given that that's the goal, how do we construct an algorithm that takes a set of input types and produces this type of partitioning? Well, the first algorithm, which I came up with several years ago, is a very straightforward algorithm I call the baseline algorithm. So the way this works is we represent the types as a Venn diagram. We ask, are any of the types already disjoint with any of the rest? If so, we remove that from the set and continue again. Is there anything disjoint? No. That means every type intersects something else, because if it didn't, it would be disjoint. So we take any type, ask what does it intersect with, we find something it intersects with, And the intersection is this region in between. And the colors are different than I imagined. Well, the colors are different than on my laptop anyway. So the three types there, A2 and not A2 and not A4, A4 and not A2, and then the intersection of the two. So, yes. So then we take those two, A2 and A4, out of the set and add in the three new types that we've derived. And then we start over again. Is anything disjoint? No. So we take any type, A4, what does it intersect with? So it intersects with A5. Well, so then we generate this, what I call the standard partition again, A5 and A4 and not A2 and not A5. Take those out of the original set and add in the new. Okay, so we just keep doing this until everything is disjoint. And at the end, we've colored all the regions like you do in the first grade with a crayon. You try to paint the regions without crossing the lines. So that's what we call the baseline algorithm. Very, very straightforward, very few lines of code, but has several problems with efficiency. The next algorithm is slightly more advanced algorithm, and what we do there is we construct a graph which represents all of the subtype and intersection relationships. So the green lines represent the fact, for example, that 2 and 4 have a non-trivial intersection, and then the blue arrows show the subtype relation. So what we want to do with this is break all of the arrows in the graph. If you've broken all the arrows, then all the resulting types are disjoint. So we start with 6 as a subtype of 1. So if we update 1, A1 to be A1 and not A6, then 6 is now disjoint with 1, so we can erase the arrow and remove 6 from the result. We have that A5 is a subtype of the three types 1, 8, and 4. So we subtract off type 5, and then we're left with just green lines, which shows that there's a relation, but it's not a subtype relation. So in this case, we have to do something fancy, and I won't go into all of the details there, but there are ways of breaking the lines in every possible case, or I believe every possible case. And one problem with this algorithm is I haven't proven that it's correct. And so there might be some topology that I arrive at that I don't know what to do about. Okay, but it works for all the cases that I've extensively tried. And it's a bit faster than the baseline algorithm, but maybe it's not even correct. Okay, so the algorithm that I want to present, that I present in the paper, is an algorithm which is provably correct and fast, or pretty fast. So again, what we do is we represent as a Boolean diagram the intersection of the particular types. And now I start with the type T, which is the supertype of all types in Common Lisp. And I traverse over the given types in some order. I'm going to go 1, 2, 3, 5, 4, because it illustrates the different corners of the algorithm. We start with A1, and we intersect the type on level n-1 with A and not A. So we have a tree that's A1 and not A1. And you notice the union of the bottom line is the same as the union of the line above, and all of the types are disjoint. We go to the next type, A2. So we traverse across the bottom line of the graph, of the DAG, and intersect each type with A2 and not A2. A couple of things happen. Every node splits in half, except for some exceptions, and the exceptions are the interesting cases. So A1 and A2 just reduces to A2. That's a nice convenience, but it's not critical for the algorithm. But we notice that A1, the complement of A1 is actually disjoint from A2. So in that case, the graph doesn't split. We just inherit the same type from the previous level. Now we go to A3. We intersect everything on the bottom of the graph with both A3 and the complement of A3, and all of the types split in half again, except, again, not A1. which is disjoint from A3. At the next level, when we intersect with A5, we notice A5 is disjoint from A2 and not A3. So you notice the green, I don't have a pointer, in the middle of the A5. The first three types in the 1, 2, 3, 4, fifth line don't exhibit this splitting behavior, that they're just inherited from the previous line because of this disjointness. So each level, we take a knife and we cut the type into two parts. The part that intersects with A and the part that intersects with the complement of A. Perhaps there's a simplification, or perhaps not. Or the knife makes no cut if either the subtype relation or the intersection relation, or the disjoint relation hold. And in any case, we remember that A is either disjoint or a subtype of the type that we've derived. So we remember the supertype and the disjoint relations as we go, which is information we're going to need later. So this is what the knife function looks like. If A is disjoint with X, we just register A in the disjoints type list. If X is a subtype of A or A is a supertype, then we register A in the supertypes list. Otherwise, we cut the type in half, and A is a supertype of one and disjoint with the other. So important is that the supertype relations and the disjoint relations are correct by construction. So we don't need later to actually ask subtype P that information. So even if subtype P is unable to answer the question later, we don't care because it's correct by construction. And finally, I intersect with A4 for completeness. And then we get a set of, is it nine different types or 10 different types, which are actually the different regions in the original Venn diagram that we showed. And we know that those are all disjoint, that they're all a subset of some A or disjoint to A. For example, X9 is disjoint from A3. Okay. So this is what the maximal disjoint type decomposition function looks like in Common Lisp. So I claim this is elegant, that we reduce the expand function over the list of given types, and with each expand, we use mapcan to map a curried version of the knife function across the given elements. So the code is very short and compact, and I actually had to translate this code into Clojure, Python, and Scala, and it's very easy to translate, much easier than the graph breaking algorithm is to translate between all those languages. So here are the types that we've derived. We have a set of derived types, which I've labeled X1 through X9. Each one specifies what are the supertypes and what are the disjoint types. And remember, in the derivative function, we need to know whether the subtype relation holds or the disjoint relation holds. And that's exactly the information we have in the table now. Which ones are disjoint and which ones obey the subtype relation. Okay, so the algorithm, I think, is elegant and understandable, provably correct, fairly easy to go back and replay this graph expansion in a more abstract way to prove that the algorithm is correct. The experimental results. So I have several, I forget the word I use, several benchmarks of sets of types in Common Lisp, given a set of types, partition them into a set of disjoint types. The first one is with member types. So the purple graph on the bottom is the new algorithm, the DAG algorithm. It's labeled Paddle there. It should be labeled DAG. So we see that after about 1/10 of a millisecond, the new algorithm becomes faster than the old algorithms for the member case. The other cases are not as convincing. So given the set of the combinations of built-in types, or these ands and ors of types that are registered in the common Lisp package. So after about, what is it, a hundredth of a second, the purple graph on the bottom becomes faster than the other algorithms. This is more of the typical case that we see here, that the algorithm called MDTD BDD, which I haven't explained, but is the fastest, but it's not so the new algorithm is not the fastest, but it's pretty fast, and it's given the fact that the code is so small, it's a good win in my opinion. In this case as well, is similar. The purple graph, when we look at the subtypes of number, it's faster asymptotically, except for this the graph there in orange. But in some cases, the new algorithm is much slower than all the rest. So I don't yet know what the problem for that is, whether could be that SBCL has special code for handling the types it knows about, and so it does a good job doing subtype P relations with those built-in types. So in summary, the DAG algorithm, I think it's elegant. So it's just 4 or 5 lines of very concise code. It's pretty fast, at least in the asymptotic cases. In some cases, it's not as fast as I was hoping. As I said before, it's provably correct. So in some sense, it's better to do something that's correct than fast.
No, okay.
If you don't need to get the right answer, your code can be very fast. And most importantly, or potentially most importantly, is we've separated the subtype P problems from the algorithm. That in worst case, we do a cut of the type into 2 types when subtype P can't answer the question we need to know. But in the end, the type that we constructed, we know the subtype or disjoint relation, so we don't have to go back and ask subtype P again in the end. Okay. So that's all I want to talk about, so I'll be happy to answer anyone's questions. Is it me who chooses, or? Yes. There was a question in.
You mentioned the ordering that you chose for the construction of the
Yes.
tree. So do you have like a heuristic for the ordering? Because probably some ordering is resulting in slower.
Okay, so the question is whether the ordering of the traversal of the types is important and whether I have tested that. No. So no, I have not tested whether the order matters, and I'm quite sure it would matter in some pathological cases. You're going to get the exact same result at the end because the
running time.
The partition is unique.
And
So the running time, whether we divide the graph early into a lot of leaves or divide it late into a lot of leaves, will determine how many computations do occur, of course. Yes. But I have tested that in the lab.
In your performance measurements, did you investigate on the impact of potential calls to satisfies and the time it takes to execute the satisfies function, and how much that influences the overall performance of your algorithm?
Okay, so the question is about, if I understand, when I'm doing the type decomposition, whether I'm testing satisfies. And so the answer is no, I haven't. I don't. Maybe I'm misunderstanding the scenario, but in doing the type decomposition, I never have to evaluate satisfies. That's only at runtime when you have an object and I want to know, does the object satisfy the predicate? So worst case, whenever there's a satisfies predicate, the type will split into a intersect A, intersect not A.
So there's a question from the chat. Is there a v/nullable function for regular expressions on sequences?
I didn't understand the question.
for regex on strings, we want that a dot b doesn't match b, and the rule is delta c a dot b equals delta c a, and something I don't know.
So it could be referring to the fact. I don't think I need to repeat this if it's from the
Yeah.
chat, right? Because one of the equations that I listed, I oversimplified for the slide. In one of the tests, there is a case you have to test whether something is nullable or not. And if I talk about that, I'll talk about what is nullable, and it's really not very interesting. That if it's nullable, you do one thing. If it's not nullable, you do another. The thing that I listed is mathematically correct, but algorithmically troublesome. That you, before you evaluate this, you need to know whether to do both sides of the traversal or not. And I think that's probably what he's referring to. Yeah. So I admit, yes, I lied on the slide to a little white lie. Yes.
One slide on the back algorithm that it appears one node saying just A5.
A5 was here, right? No. Here. Here, right?
For instance, yes. That the relationship of A1, not A2, not A3. A3. But right in the middle, almost in the middle of the graph.
So A2, A1, not A2. Yes.
Yes. Then it branches into A5 and A1, not A2, not A3, not A5.
Yes.
Don't we lose some information? I don't know.
Oh,
It
So-
seems that there has been a simplification.
so I would like to ask the question that I would like to answer and not exactly what you asked, because you're hitting on the same point. That in each case, we know that the types that we derived are either a subtype of or disjoint with the knife type, the cutting type. But when we do the simplification, we very well might lose information. In particular, we lose information that subtype P might need to reconstruct the subtypeness, or to compute the subtypeness. Yes. So I think cleverness, it's not really so clever when you look at it, it's obvious, is when we do this cutting, we just need to remember what the factors were, factors in the sense of A and B and C and D, and which ones were disjoint. So as long as you remember that, we can recover the information that we lost. Does that
Yes.
accidentally answer the question?
Yes. That means we should keep the tree.
Pardon?
It means that if we want to keep that information, we need the whole tree, not just the leaves.
Well, we maintain the information from the tree that we need. We don't really need the tree. We just need to know this list for each type, which ones were disjointed, which ones were supertypes. We could reconstruct that from the tree, yes, if we had the tree.
Question, quick. Okay, quick question. Because you've shown so many performance graphs, where is the performance being spent? Have you looked into that? Is it just a number of course to subtype P and how complicated?
Okay, the question is, do I have any more explanation about why the performance is the way it is? And no, I haven't done investigation about where the performance is being spent. That was a comment by some of the reviewers, and I should do that, yes. Should look into that.
Okay, thank the speaker again.